Greetings everyone, welcome back to Trigonometry. Time to take a little sidestep here and just throw out a couple of more applications that trigonometry can be used for. Now I've kind of mentioned this first one very briefly back in a previous lecture, and I do insist that you go back and take a quick look at that example problem. It was in the right triangle trigonometry section, and it was dealing with what we're about to talk about. You definitely want to go take another look at that and make sure that that problem makes even more sense to you now that we present this here. Okay, so without further ado, the first application is bearing. Bearing is any time you want to use some sort of angular direction to determine which way you're going to proceed. Okay, planes, boats, compasses, a lot of these things all use angular directioning. So bearing is a very common way to get a straight line direction on something. Now, of course, on larger round objects like the Earth, especially like over water, bearing has to be constantly monitored because the curvature of the Earth can, fluctuate the actual straight line bearing because you're not moving technically in a straight line, you're on a curved surface. But anyway, another topic for another day. Here we're assuming that we're moving along something either small enough to be assumed to be flat or something that truly is flat. Okay? So with bearing, of course we have the cardinal directions, northeast, southwest, and bearing can be listed in two different ways, and I've got an example for each. Okay, so the first way is you pick a main direction and a secondary direction with an angle correction. Okay, so a main direction is always either north or south, and the secondary correction direction is either east or west. Okay, so for example, this direction here is south, like I start out looking south, and then I correct towards the eastern direction. So south, 60 degrees east. See the way the implication is? I'm south and then 60 degrees east, like that. Okay? So you'll need two directions instead of just saying southeast. It's not exactly right. Okay? I'm looking south and then turning 60 degrees east. Okay? So then there's the angle, of course, in your directional. Or you can use the compass type of directioning, which uses 0 degrees as north. Now this is going to be a little counterintuitive because this is not our Cartesian system where the standard angle starts on the horizontal line. Okay? Our 0 degrees for compass type of bearing is north. 0 degrees is north. And it rotates in a clockwise direction. So east is 90 degrees, south is 180 degrees, west is 270 degrees. And then 360 is back at north again. And we typically only rotate in the positive direction because we only need each direction represented one time. We only need one cycle. We don't need to keep going around or go around the opposite way or anything like that. Okay, bearing doesn't work as generically as just angles in trigonometry. So, for example, if I tell you I'm on a bearing of 310 degrees, if I just give you a degree of bearing, then it's obviously the compass type of bearing, and then you would think of it as rotating from north until you hit that terminal direction side. Okay, so in this case, 310 degrees is pointing that way because 310 is greater than 270, but less than 360. Okay? Now, let's get a couple of applications. Lisa swims 55 yards east and 72 yards north away from her boat. Okay? So what bearing and distance is she from the boat? Okay? Now the wording is crucial here. The bearing is going to be measured from the boat, not from her. That does make a difference. Now, of course, the distance is the same no matter what. This is like someone asking, hey, where's Lisa? She's at this bearing. Okay, the bearing from the boat. So they'll turn that direction and go that way towards Lisa. Okay, so what we want to do is we want to start by drawing our cardinal directions here. Like so. And of course, north is this way, east is this way. And Lisa swam 55 yards east. So she swam this way. 55 yards. Then she swam 72 yards north. Now, of course, east and north are at a right angle to each other, and therefore this line right here is going to represent the direction and distance that we need to talk about. The boat is here, this is the boat, and Lisa is here. Okay? Now from the boat is using the original north, south, east, west directional that I have already drawn up here. Okay? However, if I were to say what is the bearing from Lisa, okay, now this is important, you would have to redraw another north, south, east, west set of bearings from Lisa's position and then calculate the angle according to that new set of grid location. Okay? That's not what we asked for here, though. From the boat, what is the bearing? So that means I'm going to be using the line around this point here to determine my bearing. Okay? So let's decide here, what is it exactly that I need to find? Well, distance, that means I need to find this distance right here, this D, the length of this line right here. Okay? And also the bearing from the boat. Well, the boat is right here, okay? And I'm going to use this kind of bearing, the north or south and then correct east or west. That means that I'm interested in this angle right here. Notice that it's not the same as the trig we've been doing exactly, because remember, whenever we're doing trig, we always draw with the x-axis. But remember, this is not the x and y axis. It just looks a lot like it. So I'm interested in this angle right here, and I'm going to label it theta. And we're interested in this distance right here. Okay? Now hopefully you've already noticed that we're just dealing with a plain ordinary right triangle. And what I have is a Pythagorean identity. D squared is equal to 72 squared plus 55 squared. Okay? Just an average, ordinary Pythagorean identity in order to calculate my distance. So I'll just be doing the square root of 72 squared plus 55 squared. And I will get 90.6 for the calculation. So D is approximately 90.6 yards. Okay. Now let's do the calculation for the bearing angle. I need to know this angle right here. Okay. Well, from what I can see, this is a north line, and so is this. Okay, this line right here and this line right here are both northern facing lines. So that makes this line right here, the distance line that we just calculated, technically a transversal, because both of these north lines are going to be parallel. This line right here makes this a transversal then between two parallel lines. So what are you getting at here, Mr. Simon? You're talking with too many words. What I'm saying is this angle right here is also theta. That's called alternate interior angles, okay? And you didn't have to do this, but I'm basically making it easier on myself to set up this trigonometry, because now I'm talking about an angle that's inside of my right triangle, okay? 55 is opposite, 72 is adjacent. Therefore, I can say that the tangent of the theta that I'm interested in here is equal to 55 divided by 72. Okay? Now, since this is an acute angle, I'm staying inside of the right triangle here. I can just use my inverse tangent, right? That was last section. Remember, we have to find angles by using the arc or the inverse tangent. So right here, my theta is going to be equal to arc tangent of 55 over 72. Let's go ahead and crunch that up. Make sure you're in degrees. So inverse tangent, 55 divided by 72, gives me 37.3758. Okay, so theta is approximately 37.358, so let's just say 0.4 degrees. Okay, so that's not the answer, remember. It asked for the bearing, right? It wants this bearing. Therefore, I'm going to use this angle, which, by the way, is this angle. I just use this to calculate it, but remember, it's technically here. I am north, and this angle corrected to the east. So the bearing is north, 37.4 degrees east. Which makes sense, right? She's north and east from the boat. Okay? Notice that I could use a similar angle. It's actually the same angle, theta, between the south and west lines here. Okay? So if it was the bearing from Lisa to the boat, from here to here, I would actually use the same angle, but it would be south 37.4 degrees west from Lisa. Okay? Next problem. Mark walks, hikes, whatever you want to call it, at a bearing, at a bearing of 220 degrees for 3 miles, and then decides to walk directly north for 4 miles. Okay? So wherever he is at that moment after the 4 miles is done, okay, they want to know what bearing and distance does Mark have to walk to get back to the original starting point. Okay? So as before, draw it out. Make sense of the situation. Start with your cardinal directions. So I've got north, south, east, west, right? And we have a bearing of 220 degrees. Now that's the compass type of direction, right? I'm going to start, my 0 degrees is on north, and I'm going to rotate 220 degrees. Well, south is 180, west is 270, so it's got to be between those two, right? It's got to be somewhere in here. Okay? So then this angle right here is 220 degrees. And it says that he walked 3 miles. So this is the starting point right here, okay? What this basically means is at his starting point, he took his compass and said, there's 220 degrees and go for 3 miles. Okay, so he rotated himself until he got to the correct bearing, and then he walked. So the length of this right here is 3 miles, 3. Then at this point right here, after he walked that, he decides to walk due north for 4 miles. Okay, so here's the question. If he's walking due north like this, okay, does he pass up the actual west line from the original starting point, or does he not? Does he stop here? Okay, well, that just takes a little bit of quick knowledge of right triangles. Notice the way this is going to be. As soon as I take this north line and I intersect it with the west line right here, as soon as this happens, this is going to be a right angle. Okay? So therefore, this distance right here that I'm finding has got to be less than this side right here. Okay? Because of the way the right angle, the right triangle works out, the hypotenuse has to be the longest side. So therefore, this side right here cannot be length 4. It has to be something less than 4, which means I'm going to have a little bit more up this way, okay? And then the total distance from here to here is 4. So this total distance from here to here is 4. Okay, now this is his final resting place for the moment. And at this point is where we want to know at what bearing and distance does he have to go to get back. Okay, so I'm going to draw the line here. And we need to mark this. Pun intended, right? We need to mark this. This is the distance right here. This is D that I'm looking for. The length of this line. Okay? And the bearing is going to be from Mark's current position, because it asks, what bearing does Mark have to walk? So I'm going to have to find an angle right here. Okay? I need to find an angle right here. Before we get to that, though, let's calculate the distance first, right? And then once we get there, you'll see we'll have some more information on the angles that we can move around and locate here. Okay, so let's get there first. So let's write down what we do know. We do know that since this is a 220 degree directional, then this angle in here must be 50 degrees. Because the whole thing to west is 270. So therefore I've got a 50 degree angle between the line that he walked and the actual west line from, if you were to go due west from the original starting point. Okay? Well, now I've got a length of a side in a right triangle that I know an angle of. That means I can calculate the two legs of this right triangle here. This right triangle here, I can use this angle with this side and sine and cosine to calculate those other two sides. Okay, so let's label those. Let's label these things. Let's call this one A. Let's call this one C. Okay, notice A plus C equals 4 from the way I have it labeled here. Okay, and then this little length right here, let's call it X. Okay? Now, A over 3 is sine of 50. Right? Okay. So that means that A is 3 sine of 50 degrees. So I know what A is. Okay? In fact, we can crunch that up. Let's punch it up right now. 3 sine of 50. 2.298. Better to have more accuracy because that's not my final answer. Okay, also I can calculate X. X over 3 is cosine of 50 degrees because that's adjacent over hypotenuse. Okay, so I multiply by 3 and X is going to be 3 cosine of 50 degrees. Well, let's see, what's that? I have 1.928. 1.928 36, so 4. You can carry it kind of far out, you know, because we don't really want to chop too closely here, because again, these aren't my final answers. In fact, I may even write X and A for these things in a minute, just to help me with these. Okay, well, I've figured out these two lengths. I'm interested in getting to D. If I know what C is, C and X also make a right triangle, a smaller right triangle up here with the D that I'm looking for. I can calculate C because A plus C is 4. So using this right here, I can confirm that C is equal to 4 minus 3 sine of 50 degrees, right? Because it's basically 4 minus A. So C is approximately what? Let's do 4 minus 3 sine 50. Notice I'm actually retyping. I didn't type in the decimal that I calculated before because I'm trying not to use any chopped answers, okay? So I retyped actual 4 minus 3 sine 50. C is approximately 1.702. That's pretty good. Let's do 1.9. That's what C is approximately. Okay, so now I'm in an awesome position to calculate what the distance is here, because I can just use Pythagorean theorem. Obviously, C squared plus X squared is equal to D squared. So my D is going to be equal to the square root of X squared plus C squared, right? X squared is 3 cosine of 50 degrees squared, and C is 4 minus 3 sine 50 degrees squared. Okay, now that's just me being accurate. You can actually, you could probably get away with doing these two decimals punched in. But I'm going to try and get this as accurate as possible. So these are the actual calculations for X and C, and I'm going to type it in just like that. So I've got square root, open another parentheses, 3 cosine 50, close that, square it, plus, open another parentheses, 4 minus 3 sine 50, close that, square it, and then close the square root. I got 2.57. D is approximately 2.57195. So we'll just let's just leave it there. And this is in miles, right? So he's got a little bit over 2.5 miles to walk back to the original starting point. Maybe that's base camp or something like that, and he's just on a hike doing these things, right? Maybe that's the case. Okay, that's fine and dandy. Now he needs to know what bearing should he travel. Well, again, just like I said before, I don't want to use the point here for the bearing. I'm going to use the point that he's at for my bearing. Okay, so I'll overlay a little north, east, south, west right here. Okay, and the bearing that I'm interested in is going to be this angle right here. If we're using the compass bearing like before, I have to go from 0 degrees north line until I get to the direction I'm interested in going. And you'll notice it's between the east and south lines here, so it's going to be bigger than 90 degrees. Okay? Here's the thing. I'm actually only going to calculate one little piece of it, and then I'm going to add the 90 here, because I already know that it's 90 degrees between north and east. What I need to calculate is the angle between the east line and the direction. But don't forget, this east line and this west line are parallel, which makes this a transversal between two parallel lines. So this angle is actually equal to this angle right here. Okay, so here's my right triangle that I already know. I know C, I know X, I know D. Okay, I prefer C and X. And I'm going to use C and X to calculate this angle right here. which is going to be the same as this angle here. And then I'll just add it to 90, and that will give me my correct bearing. Okay? So right here, let's call this angle gamma. I'll do the little, it looks like a little ribbon, right? Gamma. So the tangent of gamma is going to be the opposite over the adjacent, C over X. Okay? Now I already know what C and X are, and I'm looking for the angle. I know that it's acute, so I can get away with just doing the arctangent here. Okay? So gamma is going to be equal to inverse tangent of C is equal to 4 minus 3 sine of 50 degrees divided by X, which is 3 cosine of 50 degrees. Okay? So here we go. I have an inverse tangent, and I'm going to open a parentheses, because in the calculator you actually have to put an extra set of parentheses around the numerator and around the denominator. So when I type this all in, if you prefer, you can just go ahead and do inverse tangent of this C over this X, whatever helps you out the most. Okay, I'm going to be really accurate. 4 minus 3 sine 50. Close my numerator. Divide, open denominator, 3 cosine 50. Close denominator, close the whole thing. And I'm getting 41.4 for this. Degrees. Now remember, that's not my bearing. I'm going to have to actually take that angle now and add it through all of the other pieces. Let's see how far different it would have been if I would have used the decimals here. Inverse tangent of 1.7019 divided by 1.9284. I still got 41.4. So using these decimals for C and X here gave me the same solution for gamma. Just an FYI there. Okay. Now my bearing from Mark's current position, okay, is going to be the 90 degrees from north to east, and then that little bit more, that's the size of gamma. It's the same size there, those two angles. So basically just 90 plus 41.4. My bearing is 131.4 degrees. That's my bearing. So he needs to travel a little over 2.5 miles at a bearing a little over 131 degrees as the compass measures. Another application of trigonometry is something that we call harmonic motion. Now, very often harmonic motion is something that's not exactly the phenomenon seen in nature, but usually it's the beginning model to something that's oscillating in nature. For example, if we take a weighted spring, okay, harmonic motion is when something is oscillating, when it's moving back and forth in a pattern that never changes. Okay, typically in reality we have what's called dampened harmonic motion, meaning things that move back and forth eventually slow down unless you have something driving them, like a piston in a car. A piston's constantly moving at the same rate back and forth. Okay. In nature, you have things that oscillate, but then they eventually slow down and try to get back to some sort of equilibrium. Sometimes you can think of maybe vibrating particles having harmonic motion and things like that. But what we're going to talk about are just some examples that are very, very smoothed out, if you will, sort of like how a beginning of a physics problem would approach something. Okay, anytime you approach a problem, you start with a simple idea, and then you add in all of the little smaller details that make it more like reality. So that's what harmonic motion is. This is sort of like the beginning of an idea of how a lot of things oscillate. And then, depending on what you're applying it to, later on you can add all the finer details, like how does friction slow it down? How do you have heat gain or loss? Or does the spring act like it's supposed to? Okay, so this particular branch is just an intro, okay? But it's a very important application of trigonometry so that you can see that we don't always have to be talking about an angle. Okay, this is an application of trigonometry that has to do with the fact that sine and cosine are periodic functions, and that's all. They're periodic functions that have a wave-like form, and they can mimic certain types of motion. So this is a beginning model for you to see how trigonometry can be brought in to a lot of real-life application. Okay, so that's what harmonic motion is. We're going to have movement that's repetitive, and for this kind of motion, for our harmonic motion, we're saying that the maximum displacement is constant. Okay, so in other words, if I take a spring like this and I compress it, okay, and then let go, the spring's going to want to make the weight bounce up and down. And we're saying that there's no heat loss in the spring, there's no air resistance, there's no friction of the ball hitting some sort of tube or whatever. Okay, we're just saying that it continues in one-dimensional motion, and that's what I have here. The weight is going up and then down, but then imagine that this continues on and on. The weight's just going to keep going up and down on the spring, and nothing outside affects or changes the motion. It just stays going up and down by some amount A constantly forever until you say, okay, stop the experiment. Okay, so that's the kind of motion that we're talking about here. Obviously not totally realistic, but the idea of this kind of motion can be applied to several different things, not just weighted springs and not just pistons. I'll show you another application with temperature in a little bit. Okay, but really what I'm going for here is for you to see that we can use these trigonometric functions for things other than angles. Okay, this kind of motion is going to have this wave kind of motion. It's going to go up and down between a maximum and minimum displacement around a center. So as you can see, the displacement that this spring or whatever object is from the center is being calculated as a sine omega t or a cosine omega t. And the omega here is slightly different terminology, but it's the same idea as what we were doing when we were doing our graphs. The A is still the amplitude, which is going to be the maximum displacement that it will ever be above or below the center, or far left or far right, whichever way you're applying this. Okay, and T is going to be the time measurement. That's going to be our axis, or we'll have a time axis. But the omega here is not necessarily the frequency like we've been calling the number in front of the variable inside of the trig function before. Okay, I use the word frequency in the graphs to give you that visual idea to help you understand the way the graphs are reacting. Okay, but here this is an actual physical application that converts time into something that the sine and the cosine can convert into an actual distance multiplier. Okay, so this omega is actually more of what we would call the wave number. Okay, in this case, the omega, the number in front of the t, is used to calculate two different things. One of them you're familiar with, the period. Okay, the period of oscillation, P is 2 pi divided by omega. That should be very familiar. That's the same calculation. That's measured in seconds per cycle. Okay, so how many seconds go by if I just do one cycle? Up, down, back to center, that's a cycle. How long did that take? That's a period. It's measured in seconds that it takes to do one cycle. The frequency is going to be almost the same. Notice it's the reciprocal, omega divided by 2 pi. And that's measured in cycles per second. See, it's the reciprocal. But the implication is completely different. How many cycles go by in 1 second? If I could time 1 second, how many cycles would go by? And this is actually a concept you might be more familiar with if you've ever heard of the term hertz or studied any kind of sound wave ideas or anything like that, because that's basically what that is. Hertz or the pitch that they talk about in sound waves is all about the frequency of the sound waves hitting your ear, or the frequency of the sound waves coming out of speakers, or whatever they're coming from, right? Okay, so that's an actual physical calculation that can be used in anything that has this kind of wave motion, any kind of repetitive oscillating motion. Okay, and that omega calculates both of those, the period and the frequency of the oscillation. Okay, so that's very important to what we'll be calculating. As I said, the A is going to be the amplitude, which is going to be that maximum distance away from equilibrium. Okay, now the example here that I have has the ball bouncing up and down from a center line. Okay, and if I had never touched the ball, the thing would be sitting on the center line. Okay, so that's why it's called equilibrium there. But then it doesn't have to be up and down like this. I mean, we could be talking about a weight moving left and right, or some sort of like a hypnotic thing where somebody waves a coin in front of you left and right, and it always swings the same amount left and right of the center. Okay, anything that has some sort of repetitive motion where it has the same distance on either side of something is harmonic motion that we can apply this idea to. Okay, we're going to be talking about weights on a spring because it's the easiest thing for us to visualize that looks like our sine or cosine wave. Okay, also notice you can pick sine or cosine, and really that just depends on the situation. If you have a sine function, then you're claiming that at time 0, the beginning, you're going to start at the center. So it's kind of like you have something that whacks the weight and makes it fly upward at first, or whacks downward and makes the weight fly downward from center at the beginning. Whereas if you pick a cosine, remember cosines start at a peak, or if it's reflected, it starts at a bottom, right? Which actually, this is more common, right? Because if I'm going to have a weight on a spring, what I'm going to do first is I'm going to pull, stretch it, or I'm going to press it, compress it like that, and then let go really quick and let it just spring like this, okay? But this is the basic idea of harmonic motion, and those are the different things that we'll have to calculate, other than maybe specific distances and specific times. Those are the main things that you would be using these to calculate, okay? Like, what is the period, what is the frequency, what is the amplitude, is the maximum displacement, what is the displacement when the time is some certain amount, or at what time will I be at this displacement? Those are the kinds of questions that you can expect from this kind of application. Let's finish up with a couple of applications that use trigonometry outside of angles, right? In other words, not using angles as part of the trigonometry, just the fact that we can use sine and cosine as cycling periodic functions. Okay, first application is the one that we just talked about, harmonic motion. Imagine the spring that we talked about oscillating around an equilibrium. So you have some, like if you just let the spring rest, right, and the weight hangs there, that's equilibrium. Okay, so the weight is now bouncing around equilibrium, some maximum height, some maximum low, and it just keeps going and going and going until you stop the experiment. Okay, and it oscillates according to the equation -6 cosine 7 pi t. And d is measured in inches above and below the equilibrium, and t is measured in seconds as the amount of time as it's passing throughout. Okay, First, describe the weight's starting point. Okay? Well, it's a cosine, right? The fact that it is a cosine and it's a negative. That's indicative right there. Okay? So if I were to draw this graph, right, like this, if I were to draw the graph, it would be a negative cosine, which means it would start like this. Right? That would be my reflected cosine. And then, of course, it would continue on in that same pattern, so on and so on. So describe the starting point. It would start at max displacement below equilibrium, right? It starts at a bottom. In other words, this is an application where somebody grabbed the spring, stretched it all the way down, to the maximum displacement, and then the experiment starts as soon as he lets go, right? He lets go. Okay, now the experiment started. So at the start of the experiment, the weight is at the maximum displacement beneath. That's what a negative cosine is going to do for us. Okay? What is that maximum displacement from equilibrium? Easy. That distance right there, right? The amplitude. Distance is measured in inches, so we'll say that it is 6 inches max displacement. Okay? What are the period and frequency of the oscillation? Well, remember, we have actual formulas for those. So the period is going to be 2 pi divided by the omega, which here my omega is 7 pi. So that's 2 pi over 7 pi, which is going to be 2/7. Now remember, period, okay? Period is measured in a period of time. So this is 2/7 of a second per cycle. So 2/7 seconds per cycle is my period. So after 2/7 of a second, it's already gone through one cycle, right? So at here, 2/7 of a second, it goes boom, boom, right? All the way up, all the way down. That's a cycle. One whole cycle, all the way up, all the way down, okay? That's a cycle right there. That's one cycle. So imagine, I can't even move my hand fast enough, but it does it in 2/7 of a second, right? From bottom, it goes bam, bam. And that's like 2/7 of a second. But of course, my hand moves not quite that fast, okay? And then the frequency, right? The frequency is exactly the reciprocal of that. 7 pi divided by 2 pi, right? 7/2. And that's cycles per second. 7/2 is 3.5. Okay? So every time you click it and go 1, 2, 3. When I go 1, as soon as I have said 1 second, it's already done 3.5 cycles. That's what 7/2 is. That's the frequency. 1, 2, 3, half. And that's a second. Okay? So it's moving fast. At what time is the weight at maximum displacement above equilibrium for the first time? Well, it starts at maximum displacement below. That's why it helps to draw this out and to understand this other stuff first. Okay? Well, so when does it hit this maximum point right here? That's what it's saying. Maximum displacement above is at this peak. When does that happen? Well, one whole cycle is this, right? How long does that cycle take? 2/7 of a second. The high point is exactly halfway through a cycle. It's going to take 1/2 of a cycle. 1/2 of a cycle. 1/7 seconds. Okay? Now another one. This isn't necessarily harmonic motion, but imagine a really simplistic version of temperature. And for the most part, temperature does, do this kind of thing, but it's not as accurate as every day from year to year to year. Like July 20th every year is not the same average temperature. But let's say that there's a city where it does happen, that every year this city goes through the same set of average temperature distributions for every day. So January 1st is the same as the next January 1st, is the same as the one before it, right? And April 30th is the same as the next April 30th as the one after that. At every time of the year, those happen to always be. And it's just sitting there oscillating between those temperatures constantly, okay? So the maximum occurs, right? The maximum occurs at July 21st of 95 degrees. And the minimum of 25 degrees occurs on December 21st. Okay? So it wants us to make a cosine model of this. Now, this is going to be something that can do more than just the way this one is set up here. Okay? The temperatures and the days are actually shifted. Okay? So here's what we're going to do. We're going to say that we have some sort of temperature distribution, and 0 right here is, day 1, okay, is January 1st. Day 1 is January 1st, right? So then the very end of the year, right, the end of the year, December 31st, is day 365. Okay? So then by the time it goes from December 31st back over to the next January 1st, right? The distance from there to there is 365 days. So it takes 365 days to go through one cycle. And it doesn't matter, guys. You don't have to measure it from peak to peak or bottom to bottom or middle to middle. You can pick any point on a sine or cosine. Okay, so I just happen to pick January 1st. It's easy to talk about. To the next January 1st is 365 days. Okay, so one cycle of temperatures has a period of 365 days. Right? Okay, so the thing that I'm making here, we'll call it temperature of X, where X is measured in days. Okay, my X-axis here is going to be measured in days. It's going to be A cosine B times X minus some horizontal shift plus some vertical shift K. Remember, that's the generic thing that we talked about when we were graphing sine and cosine, and it's how we construct sine and cosine models. I just didn't have to worry about the minus h and the plus k when we were dealing with the harmonic motion over here, because there is no displacement. It starts wherever you want it to start, right? And I don't have to do the plus k because I can basically call the equilibrium 0 no matter what for these kind of applications. But in something generic like this, obviously it's been shifted upward from 0, right? Because 0 isn't even included in my temperature range, right? My range is from 25 to 95 degrees. So it's obviously been shifted upwards, right? And here's 25 and here's 95, and it's bouncing in between those two temperatures. Okay, so we're going to figure out what A, B, H, and K are. First of all, we can really quickly figure out B because we already know that our period is 365, right? Remember, our period is 2 pi divided by B. Well, that goes the same way. You can actually interchange those two. B is also 2 pi divided by the period. Right? We talked about that back in the first graphing lecture too. So I'm going to calculate my B. T of x equals some number times cosine of 2 pi over 365 times x, and then I'm going to have my shifts in there. So this is my model. I've already figured out one of the pieces of it, right? 2 pi over the period, 2 pi over 365 is now within my cosine there, okay? Now, incidentally, in case you didn't see it, the cosine is actually encapsulating all of this, right? I'm actually doing the cosine of all of that. Typically, we don't, write those extra brackets, but I'll throw them in there just so that you can see. All right, so then let's figure out what the horizontal shift from x is right here, okay? Since we're doing a cosine, right? Remember, a cosine likes to start on a peak, okay? Well, where is the highest temperature occurring? Remember, it says right here, July 21st. So right here, if this is July 21 right here, if that's whatever day that is, then that's going to be the peak of the cycle. Like that. That's going to be the peak. So guess what? That's my shift. It's been shifted from the beginning point over to that point. So if I can figure out what number day July 21st is, then that's the number of my shift into this thing here. Okay? So let's calculate that. Let's calculate how many days in July 21 is throughout the year here. Okay? So we're going to do January has 30 days, right? 31, I mean. 30 days have September, April, June, and November. February is going to have 28, right? Okay. And then March, 31. April, May, June, and then we don't go all the way through July, right? We go to the 21st day. Okay? Now, we're actually doing the distance here, right? So I actually have to shift that many days. So let's do that. Let's add it up. 31, 28. Well, let's see. We could almost do this in our heads, couldn't we? I could take these two right here and make this a 30. So then that would be 30, 30, 30, 30. And then another 30. That's 150, 181, 202. Okay? Now remember, we're shifting up to that day. So I just realized what we need to do here is 20. We're counting January 1st as a whole day, and then we're shifting to July 21st. So I need to shift the days before it and then land on it. Okay? So we're looking at 201. Right? 30, 30, 30, 30. Yeah, that's 181. 20 is 201. So my shift shift 201 days. So then this is going to be minus 201. Okay, now the other two, the amplitude and the upward shift, I can figure out at the same time. I need a cosine that bounces in between, right? A high of 95 and a low of 25, right? So the center of these two is going to be my shift, right? That's my center. That's going to be my shift upward into the positive. And then the distance from that center in either direction is going to be my amplitude. Okay, so let's find that center first. The center is going to be the average, 95 plus 25 divided by 2. So that's 120 divided by 2, which is 60. So then my shift up from the center, whoops, put the wrong one down. My shift up, I should have plus 60 here. And then the amplitude is going to be how far is it from 95 to 60 or from 60 to 25, right? So 95 minus 60 is 35. Also 60 minus 25 is also 35, right? So there's my amplitude, 35. So there's my answer right here. This is the answer to find the model, okay? So we have modeled this oscillating temperature, average temperature, right? Oscillating average temperature of this city, given these pieces of data that they've measured year after year after year, okay? Now, sometime later, we can do even more with this once we talk about solving trigonometric equations and doing other things with the graphs. We can actually take this equation and use it as a prediction day by day by day. Like, what day is the temperature going to be this? And if I know what day it is, what temperature is it going to be that day? Things like that, and so on and so on. There's just so many things, and then eventually we can talk about, does it shift due to leap year? And then you grow your model with your small details after you start with the basic idea. Okay. So I hope this brief lecture on a couple of different applications has just broadened your mind on the things that we can do with trigonometry and not just angles, things that oscillate as well.